What is up, Mathletes? So I want to make this video for you to give you a recap of section 3.2. All right, so here's what we're going to talk about. We have this function here, right? And so what I did is I had decimals go ahead and graph it for you, right? And what we're looking at a whole bunch of things. We're trying to see, you know, where it has intervals, where the intervals show the graph increasing or decreasing. All right, and that's the first thing I want to look at. How do we find where the graph is actually increasing or decreasing? All right, so to do that, what we need to do is take the derivative of this. All right, so we take the derivative of this, and this is going to help us find these intervals. All right, and what you do with that derivative is you set it equal to 0. And what that helps you find are critical points. And remember what critical points are. They're going to tell us where the graph is, increasing if we have a peak, or if you have a valley, or if you just have a place where it's changing, going from, increasing to decreasing. So that's what our critical values help us do. All right, so let's go ahead and let's actually do the calculations for this. All right, so what we did is we took the 6x squared plus 24 and you set it equal to 0 and you solved. All right, and when you solve this right here, you get two answers. You get -4 and you get 0 after you set it equal to 0 and you do that math. All right, so there's two ways of looking at this. You could do it algebraically like I've taught you, or you could just look at the graph, right? So here I've graphed 6x squared plus 24x. And look at the zeros. You have one at -4, which is right here. And you have another 0 here at 0. So this is going to divide our number line into 3 intervals. So again, what we're looking at is where intervals, right? Where is the function positive? Where is it above the x-axis? Which you could see here and here. So to the left of -4 and to the right of 0. And where is our function negative? Which is down here. Mathematically, the way you're going to be doing this is after you have these critical numbers, you pick a number that's less than -4, which here I plugged in -5. And look where I plugged it in. You plug it into the original function. And when you do this, when you plug it into the original function, all you care about if your answer was positive or negative. In this case, we get a positive answer. And so what that means is that to the left of -4, our graph is going to be increasing, right? It's going to be going up. And if you were to look at the original function, you would actually see it increasing. To the right of -4, right, we plug in a number that's between -4 and 0. So we plug in -1. Look at where we plug that in. We plug that in to the original function. So I plug in -1, and my answer is negative. So what that tells me, between -4 and 0, we're going to see the original function falling, right? It's going to be decreasing. The graph is going to be going down. And then we have our last region over here. So that critical value was 0. We pick a number greater than 0. So I picked 1. Again, plug into your calculator and you're going to see you get a positive answer. So that positive answer tells me to the right of 0, our graph is going to be increasing. All right. So again, looking at the graph using decimals, you're going to see this. So you could do it algebraically like we've done here, or you could do it graphically like I've shown you here. All right. And so notice when the graph is increasing over here, and then at -4 hits its peak, and then it goes down, that's called a relative max. So at -4, we have a relative max because our graph is increasing and then it decreases. So it has a maximum point, a relative max. So to find that point, you take that -4, that critical value, and you plug it into your original function. And that's how we get the 65. So again, I'm just trying to summarize the steps in terms of what you already have done, because it's a long process. Over here at 0, this is another one of our critical values. What you have seen is if I plug in 0 into our original function, you get a height of 1. So how do I know if that's a minimum or a maximum, a relative min or max? Well, look what's happening. Your graph is going down on the left-hand side of it, and all of a sudden it starts going up. So if it's going down and then up, we see that that's a relative minimum. So this point 0, 1 is a relative minimum. All right, so that's how we take care of our intervals of increasing and decreasing, and that's how we find a relative min and a relative max. So all we have done so far is take the first derivative, right? So let's continue the march. So now let's talk about concavity. So notice we have the first derivative right here. This was the first derivative. So to determine concavity intervals, what we do is we need the second derivative. So we're going to take the derivative of this function right here. So we're going to take the derivative once more. And so I've done that right here. And what we do, just like we've been doing, is we set it equal to 0. And we solve this. So when we solve this, right, we go through the math and we solve for x. You get x is -2. So what that's going to do, as you see in our graph here, here's -2. That's going to split our number line into two intervals, right? So we need to test these points out. We need to see what's happening. So what we're going to do is we're going to pick a number that's less than -2. And depending on what we get, that's going to tell us about the concavity. So I picked a number less than -2. I picked -3 and I plugged it in. Notice that gave me a negative number. So that means the concavity here is concave down, because our answer, right, when I plugged it into the second derivative, right, this function right here, we got a negative result. So that tells us that our graph, the concavity to the left of -2, is concave down. Then I pick a number to the right of -2. When I plug in -1, right, that's the number I chose. Notice I get a positive. So that tells me on the right-hand side, the graph is concave up. All right, so notice to the left, it's concave down, and to the right, it's concave up. So what's happening is the concavity changes. And whenever we have the concavity changing, that right there, that point -2 is called our inflection point. So in the homework, when they ask you to find the inflection point, what you're looking for is to see when is the concavity changing. And so this is a great example of when the concavity is changing. So how do I find that point? Well, you take that -2 and you plug it into the original function of f. And so when we plug in -2, you get 33. All right, so this is our inflection point. Alrighty, so what I'm going to do is I'm going to label all these into our original function so you can actually see how all these look. All right, let's take a look. All right, so let's put all this together. And so what I did is I graphed the original function, f of x. So I had decimals graph this for us. And just with this graph alone, we could answer all the questions. So I didn't even need to do any of that math, but again, it's helpful. So look, where's my graph increasing? Well, it's increasing right here to the left of -4, and it's increasing from 0, all the way to infinity. So there's where my graph is increasing, and that confirms what we got earlier. Where is our graph decreasing? Well, it's decreasing from -4 all the way to 0. So there we see where our graph is increasing and decreasing, and that confirms what we got earlier. Concavity. Let me do concavity here in green. Where is my graph concave down? Where does it look like a hand kind of facing downwards, like I'm spilling a cup of water? Well, we could see from -infinity all the way to this point of -2 right there. We can see our graph is concave down. And remember what we found earlier. We found this point of inflection. Let me go ahead and make that really dark. So this point right here, of -2, 33, that's our point of inflection. That's where the concavity changed from concave down, and all of a sudden it changed from concave up. And so this area to the right here, let me do in yellow, let me highlight it in yellow, from here forever, right, we see it's the graph, the function is concave up, right, that slope is increasing. And so again, this goes hand in hand with everything that we found doing by hand. So again, you could always answer those questions just by looking at the graph, but it's nice to have some algebraic way of confirming all that. All right, folks, so hopefully this helps out. Keep sending me your questions, and we'll see you in the next video. Peace.